All right, I've worked with some students on Counting 2 problem 7, and I think that it is unnecessarily hard, or that it's hard in the wrong places. And so the purpose of this video is to alleviate that and make it into a problem that is good for you to work on. All right, so Counting 2 problem 7 is this problem. It says count the number of functions phi from this set to this other set that are not onto. All right, so there's a few things that are kind of wrong about, or non-standard. Non-standard for this class, the way that I've set things up. This phi here, this is just, you could just think of this as saying f. It's just a symbol, a name for a function. So think of it as f. I think people are more comfortable with f. Now, instead of these these parentheses here, and so on, they should actually be the set brackets. So it should say something more like this. And then, now that it's a set, this is the domain. This is the target. All right, now this is the problem that I have. The randomization for these problems on WebWork will give you different domains and targets. And it's kind of weird that we have this ... here when there's only one number missing, right? So they could have been written like this. And like so. The reason for that ... is that the randomization chooses the number of, so at random it's chosen the number of numbers that are in the domain and target. And so some students will have a ... when there's 6 numbers. Some students will have a ... when there's 5 numbers. Some students will have a ... when there's 4 numbers, like I had here. You may have 7 numbers, you may have 8 numbers, I don't know exactly. But in any case, the domain and target are finite. So, and they have the same number of elements. That's important. Okay, so because they're finite and they have the same number of elements, we really don't need to worry about what the numbers are, what the actual numbers are here. And we could rewrite this as f x1, x2, x3, x4. Now you may have 5 numbers in your domain, and so then you would want to have x1, x2, x3, x4, x5. You may have 6 numbers, then you would want to have x1, x2, x3, x4, x5, x6, etc. Here I can rewrite this as y1, y2, y3, y4. All right. So now that we've reformulated this, now the answer to the problem, I'm not going to give you the answer, but I want to give you a strategy for solving it. The answer to this problem is going to be the number of functions minus the number of onto functions. So what you want to do is you want to first count, so use the counting techniques that you've learned in Counting 2 to count the number of functions, and then subtract from that number the number of onto functions. That will give you the number of functions that are not onto. But there's another little trick here. Now notice that the domain and target have the same number of elements. However many elements you have in your domain will be the same number of elements that you have in your target. And so since the domain, the cardinality of the domain is equal to the cardinality of the target, the number of onto functions is equal to the number of one-to-one functions. And counting the number of one-to-one functions is much easier than counting the number of onto functions. So let me cross that out and put in one-to-one. So your answer is actually going to be that you are going to count the number of functions and subtract from it the number of onto functions. Let me show you a way to go about doing this. So first, let's look at number of functions. So think of it as a table, domain and target. So what you want to do is you want to think about how many choices, number of choices here, number of choices for a y value there, number of choices, number of choices, number of choices. Now I'll leave that to you. But one thing I will show you is that remember that a function from our domain, right? Domain and target to our target. We could have everything going to y1. That's okay. That's still a function. Oops. We could have something like this. That's still a function, right? Lots of choices for x1, lots of choices for x2, etc. All right, and so you want to do the same sort of thing with one-to-one functions. Okay, now we'll look at one-to-one functions. With one-to-one functions, remember that x1, with x1 you can, let's say you're going to start with x1 and say, okay, well, where am I going to send x1 over to? Well, there's 4 choices, right? You can send x1 there, 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 or there. But what happens? Let's say that you choose that x1 is going to go to y2. Now, how many choices do you have for x2? Once you've chosen x1 going somewhere, how many choices do you have for x2? Once you choose where x2 is going to go, let's say you choose x2 to go over here. Now, once you choose, now you've chosen where x1 has to go and where x2 has to go. How many choices do you have for x3? And so on. That'll allow you to count the number of one-to-one functions. All right, good luck. I'll leave it up to you. I hope this helps.